Segment length scaling. So now let's have a look at individual segment scaling. So if you wanted to give the animator the control over the length of the upper and lower arm individually, so it can be used in animation. So for this, let's first have a look at the IK. So let's move the IK control to a specific position and set the switch to use IK completely. And then if we go to our IK solver panel, you can see that we have the upper and lower length for the IK solver, and we can simply change these lengths because these are the basis for every calculation in the IK solver and the soft IK setup. So if we change these, we can change the rig like we're changing the default rest poses of the length. So if we check our settings, yes, if we graph the inputs to these nodes, and then Maya goes all the way there, we can see that these are based on the measurement between the original guides. So graph these, press F to focus again. So you can see the upper, lower and hand guide distances are measured and they produce the initial lengths. And what we now can do, very simple, is add a attribute on our settings control. I like to add these individual scalars for upper and lower arm to the settings control for the arm. You could, for example, set the scaling on the IK hand control, and then for the FK maybe use the scale components of the controls. But I like to have them in one place, and as well shielding it a little bit from the animator so they don't use it too often, so the character goes off model. But having it available if you need it for a specific pose to use it. And then I also combine the scaling for the upper FK and IK to be the same scalar value. You could split it into a separate IK or FK scale value, but in my opinion, when you scale the IK upper arm and you switch to FK, you probably want the FK arm to have the same scale as well. And if not, you can always animate the scale in the transition as well. So I'm going for a single scale value for IK and both FK. So let's add these. So add an attribute. Let's call these upper length scalar. And then write it correctly. And make it a float with a minimum of 0 and a default of 1. And add this. And then as well add the lower length scalar in the same manner. Set the minimum to 0 and the maximum leave unfilled and the default to 1. And then if we now add the control, Maya keeps just framing everything when you add an object or graph a connection input. I don't know why, but it's very annoying. But you can just press the F key to focus again where you were working. So if we now take the upper scale length and we multiply it by the initial upper length, then everything in the rig adjusts to that new length. So let's make a multiply node. And then in the first input, let's take the distance from the initial length and then multiply it with the upper length scalar. And now we can take the initial length output and plug it into the output of the multiply. And let's check if we have another connection. Yes, so there is another connection going to the initial length of the arm. So we have to reconnect that plug as well, because this is the added length of the upper and lower arm together. If I graph the input, you'll see it goes to both. So we have to update that connection as well. So don't forget to check if there's any other downward connections that you need to replug. So let's call this the left length manual scale. Let's leave it at that for now. So, and then we can duplicate, and do the same for the lower arm. So let's call this lower length manual scale, and then input the distance from the lower initial length, plug it in, and then take the lower length scalar, plug it in, and then replug the output connections of the lower initial length and plug them into the output of the manual scale. So now we have introduced the scaling for the IK. And if we now look in the viewport and we select our control, and if we use our upper length scalar, we can see the segment scaling. Of course, the mesh isn't scaling because it has a fixed length, but we can fix it. So let me fix that very quickly. Okay, so I reset the length of the arms to be unit length, and then I connected the upper and lower lengths to the scale X value of the arms. So now we can see that if we scale the arm, it still works. However, if we go into the overstretching, the soft IK starts kicking in. So the soft IK scales the limb as well. So if we want to have that as well, we can just move these along, and instead of the input upper and lower length, we can use the soft IK scaled upper and lower length. So if we use this one and this one, you will see that the even the soft IK scaling is taken into the arm segments. So now we have IK scaling, individual arm segment scaling working with the IK, and the soft IK also still works. So maybe while we're at it, we should create an enabler for the soft IK. So maybe we should have that. We have the enable IK stretch and the soft IK start, but we do not have the soft IK enable. So let's add the attribute for that. So let's create maybe let's just make an on-off switch. So a Boolean value which says enable soft IK. Okay, and then we're going to use that. We already have this. Yep. We're going to use this to multiply the scalar values. So let's maybe just put it where the end of the soft IK chain is. So we have this. So when we enable the soft IK scalar, we want the output to be the scaled value. And if we disable the soft IK, we want the output to be 1. So the original length stays the same when multiplied with 1. So what we can do is use a max node for this. And if we have the soft IK enabled to on, then we want to use this value. So let's use a not node to reverse it, because the on state true is 1. So if we do a not node, then it reverses it to false, which makes a 0 a 1 and a 1 a 0. So it's a Boolean operation. And if we now take the output of this node and plug it into the max, we'll see that the output is 0. And if we now plug in this into the second input, then if we have the soft IK enabled, then we'll use the maximum, so it's the value that's coming from the soft IK scalar. And if we now enable soft IK, let's disable it, so put it to off, then the max value, or the soft IK attribute via the not node, will become a 1. So it will always use the 1, because the 1 is larger than the scalar value, and this scalar value will never be larger than a 1, and it will never be smaller than 0. So this way we can toggle the enabling of the soft IK. We could have used an attribute name that says disable soft IK, but I like the enable method of writing it, and the not node will only be once evaluated when the file opens, because this is not an attribute, it's going to be animated. All the attributes on the settings node are static values, do not change on animation time. So this is a nicer way to write it, I think. So and we now take the output and plug it in here. We already see the scale changing, and we can do the same for the lower. So we make another max node, and then we take the same output of the not value, and then we take the output of the soft IK scalar, and then we plug this in here. So now we will see that we do not have the soft IK. So if we now set the upper length to a larger scale, you will see that it will not get shorter when it almost collapses on itself. And if we now enable the soft IK, you see that it does, because it's enabling the smoothing of the height via the soft IK setup. Okay, so let's reduce this to its original length and then rename these nodes very quickly. So I've renamed them to left arm disable soft IK, and then the upper soft IK scalar enable and the lower soft IK enable scalar. So we have added that as well. So now let's look at the FK scaling of the upper and lower. So the scalar of the upper FK arm segment will have to be done in the buffer offset of the FK control, the lower FK control. So if we take a look at this, we see that the world matrix of the FK control is generated, or the input world matrix, so to speak, of the lower FK control is generated by multiplying the buffer or parent offset matrix output with the upper FK world matrix of the control. So in this node, if we look at the attribute editor and we take a look at this node and take a look at the first input, which is coming from the parent offset matrix or buffer group, and we can see that the translation in the decomposition tab or in the matrix tab, that the translation is responsible for the length of the arm segment. So we have to modify this value while keeping all the other values the same. And now the rest length, or the rest arm, is in a straight position. That's why there is no rotation values in the matrix. If we were to introduce a small angle in the rest pose of the arm, then we will see that there is a lot of values here. That is the rotation of the lower arm buffer matrix. So let's reset this to a straight arm, and then let's take a look at how we can modify this matrix. So basically we want to change only the translate X value of the incoming matrix, and of course we have the 4x4 matrix node where we can input the all the individual matrix values, and a composed matrix comes out, or actually just a matrix set with these values. There's no math going on, it's just basically directly setting the values in the matrix array. But we do not have the inverse of this node, unfortunately, in Maya, where we can input a matrix and then output all the individual parameters, which is kind of a shame, because it would be very useful in this scenario, where we could plug all the plugs from the basis vectors straight into each other and then only modify the translate X value. I created a node myself. It's called the P matrix rows, where you can input a matrix and then you have all the essential row information available. Of course, I left out the W component because it's always 0, 0, 0, 1. But this is not a Maya default node, so I'm not going to use it. So unfortunately, we have to use a little more nodes, but still, I think the overhead is minimum because the nodes are very simple. So what we can use for this is, we have 3 nodes. First, we have the translation from matrix, which is basically taking the 4th row of the matrix and then outputting only the X, Y, and Z components of it. So basically it's returning the 3, 0, 3, 1, and 3, 2 values of the matrix that's plugged into it. So this way we can get at least the translation in one go. And then we also have the row from matrix, which returns 1 row. So if we input the matrix and we set it to 0, then it returns the basis vector X, So you will see it has an X, Y, Z, and W component, so it returns a vector 4 data type. And as well, we have the axis from matrix, where you can input a matrix and then choose which axis, and then it returns a vector 3 with the X, Y, and Z component of that basis vector. And you can also get the negative one, so if you choose negative x, it will return the basis vector x components and then scaled by -1, so it's negated. So we're not going to use this. We're going to use the row from matrix, and we're going to use it 3 times, unfortunately, because Maya doesn't give us any other options. So we plug in the matrices, and then we choose the zeroed index for the first, so the base vector x, and then we use input 1 for the basis vector y, and input 2 for the basis vector z. Of course, we could have also used a row from matrix with the input set to 3 to return the translation vector, but we are using this because it's more direct. Even in the name says it's more explanatory if you select the node what it does, so it's easier to read. And then what we do, we are going to use a 4x4 matrix to recompose the matrix. So we're going to just plug in directly the basis vectors into the matrix. So we're not going to modify it, and it will not take any computation, because basically this node is just setting the values directly from the matrix onto these attributes, and there's no calculation needed or anything whatsoever. So it's pretty fast. It's only the overhead of the node itself. And then for the translation, we're only going to use the translate x, and then we're going to scale it with the appropriate scale value that we generated. So let's bring that in. Let's get the settings control and add it to the graph. Yep. And then let's see where we were. We were here. Maya does this sometimes. It just catches the 3 button in the search bar, and it's quite annoying. So we're here. So now what we need to do is create a multiply node again, and then we're going to multiply the x output of the translation from matrix, because that's where the length of the segment is stored, because it's the x translation relative to its parent, which is oriented in the with this x direction in the direction of the next joint. So it's only a translation on the x direction, on the x-axis. So then we are going to take the upper length scalar and multiply it with the translate x value, and then we are going to output that directly into the matrix. And then we have a new matrix which has the same basis vectors, so the same rotation, scale, and shear, and then we have scaled the translate x value. And then what we can do now is the original parent offset matrix. We can take the outputs from there, which are not going to the nodes we just created, and plug them into the reconstructed matrix. So like this. And now if we take the settings control and scale the upper length, you will see that the FK is scaling as well. So that's for the FK settings. So now let's rename these nodes quickly. Okay, so I renamed them to axis X, axis Y, axis Z, and DT, and then this is the TX scaled, and then the new constructed matrix is the parent offset matrix manual scale, or buffer matrix manual scale. So we have to do the same thing for the lower. And you can see now why it would be very useful to have the inverse of this node, because then these 4 nodes would only be 1 node, and even though these are only directly setting values just as this and quite fast, it's still 3 extra nodes in the overhead for scheduling these nodes in the evaluation graph. But let's do the same thing for the hand FK control. So again, we're going to do a row from matrix 3 times, and then we plug in the matrix, and then we set the input to 0, 1, and then 2, and then we do a translation from matrix, plug in the parent offset matrix as well, and then we create the 4x4 matrix, and we show all the attributes, and then we take the values and plug the basis factors directly into the 4x4 matrix, like so. And the Z as well. And I'll collapse them to take less space. And then for the translation, we again create a multiply node. And then we input the translate x, where the length of the segment is stored. And then we multiply it with the lower length scalar. And then we plug that into the tx value of the matrix, and then we take the output connections of the original parent offset matrix or buffer matrix, and then we plug them into the newly created matrix. And now again we can have the lower length as well scaling for the fk. So let's rename these nodes as well very quickly. So I rename them in the same manner, so axis x, y, and z, and the t, then the tx scaled, and then the parent offset matrix manual scale, or buffer matrix manual scale, if you like. So, and that is the individual length scaling of the ARM segments. However, there's maybe one more shortcut that we could take, because now we are taking the translation from the offset matrix and then multiplying the tx and plugging it into the new matrix. However, for the IK setup, we already took the original lengths, which we measured from the guides, and multiplied it with the scale, and then used that in the IK setup. So as well, we could have reused these nodes, because we're using the same scale for IK and FK anyway, and these lengths are calculated as well. So if we, for example, add in these nodes here, let's see, we could say that instead of, let's collapse these into their small form. So instead of doing these two nodes, taking the translation and scaling the tx, we could say, okay, we already have this tx value, we can take this directly and plug it in here, and then we can ditch these two nodes. And the same for the lower, we have already the, where is it, here, the lower length scaled, so we can ditch these two nodes and plug this one directly into here, and then the scaling of the lower and upper arm still work the same way. We could do that to save another 2 nodes, so let's do that for now. Just delete these and delete these as well. So we have removed 2 more nodes from our graph and optimized it a little bit further. There is one alternative way, which we're not going to use, but I'm going to show, which can produce the same result, but is a little bit slower, and that is via the pick matrix and mult matrix nodes. So if you create a pick matrix node, you can plug in a matrix, for example, the buffer matrix, the parent offset matrix here. And if you then, for example, disable the translation, you would end up with a matrix that just has the scale, rotation, and shear left. So basically the basis vectors x, y, and z untouched, and the translation vector reset to its default values, the default values from the identity matrix. And then you could construct the translation matrix the same way via a 4x4 matrix. So then you would create a 4x4 matrix, show all the inputs, and then you would take the scaled value of the length and then plug it into the tx value. And then you could use a mult matrix node to add the translation to the rotation matrix, like so. Plugging this in here and this in here, and then the output would be the same matrix as this matrix. So if we look, for example, in the this matrix, you will see that it has the same value as when we plug in. If we plug in this matrix instead, it is exactly the same matrix. Only it is more expensive to calculate, because this is a multiplication of two matrices, and here we are not multiplying any matrices. We're just simply setting values and connecting those attributes, and no multiplication or addition is performed. So apart from multiplying these two matrices, we can also use the add matrix. So what this basically does, it just takes every single component of the matrix and adds it to the component of the other matrix. So the basis vector x component is added to the basis vector x component of the second matrix. But this has another issue you have to take into account. For example, if you now add this matrix and add this matrix as well, and we break these connections and use this as a information node, so to speak. If we now look at the matrix, it has produced a matrix with scale of 2, and if we look at the matrix itself, you see that all the identity or diagonal values have a value of 2, because this matrix has a value of 1 in this position, and this matrix has a value of 1 in this position as well. So if you wanted to do this with an add matrix, you would have to remove all the ones from the 4x4 matrix, and as well from this position, because we cannot modify the values in the pick matrix other than just disabling or enabling certain transformations. But if we can disable them here, so we just basically only set the translate x value, and if we now add these together, you see that we end up with a normal matrix. However, this takes 3 nodes, and this takes 4 nodes, but the pick matrix can also be a node that is slower and takes more calculation, because it has to check what to do. If you only disable translation, I do not know the code inside of this node, but I presume that it just leaves the basis vectors x, y, and z intact and just resets the translation vector. But I'm not sure. It has to do some checking with if statements, which can cause branch prediction issues in the CPU, so possibly slow things down, depending on the compiler and how the CPU handles these instructions. So better to be safe than sorry, and use this setup instead. So, for example, if you use the pick matrix and if you disable rotation, for example, it resets the basis vectors to its default values and then applies the scale that it distillated from the input matrix. So it calculated the length of every basis vector. So it has to do a multiplication and a square root to get the length to be multiplied with the basis vectors that are the default basis vectors if you disable rotate. The same goes for share. It has to do some dot products to get the share values between the basis vectors. So disabling or enabling these values have different results in operations that need to be done internally. So if you have a basic matrix modification like this, where you just need to keep the basis vectors intact and only want to change the translation, or maybe do something else that's quite simple, you can better just decompose the matrix or pick apart the matrix like this and rebuild it than to use a pick matrix. But I wanted to show you anyway how you could do it with the other Maya nodes. But for now I'm going to stick with this setup. So let's remove this, and then we're back to our operational rig. So let's reset our values here. And then, because we're not going to use the scale value of the FK controls for the length, we're going to lock and hide that value. So the scale X we're going to lock and hide. And for now we will just lock the Y and Z scale. And in a later part in the series we will probably use these for thickness scaling of the arm if we want to set that manually. And the same goes for the IK control. We can lock and hide the visibility. And the scale we are going to lock for now, as we will not use it at this point, maybe later on in the series as well. With the joints, skin joints, we can move these to the joints group in the module, and we'll leave these outside because they're just temporary stand-ins. So before finishing up, there's one more thing we need to do, and that is check the global scaling. And my assumption is that it's not working, so let's check. And if we are in FK modus, then, well, sure enough, something is going wrong. And if we switch to IK mode, then, well, it is all over the place. The length gets very long when you scale the rig up, and when you scale it down, the arm gets bent without it needing to bend, because the arm is still straight in the FK setup. So let's check where this is going wrong. So if I go to the IK solver tab, and we are going to the arm upper length, for example, we can see that the initial length is still set to 4 and the manual scale set to 1, so this is alright. And the IK stretch is okay. And here we have a problem with the clamped length, because the length of the arm, we are adding the length of the arm multiplied with the manual scale as the arm length, which is still the length of 4, so a total length of 8 for the arm in its default pose. But because the rig is scaled, we are having a current length which does not coincide with the unscaled length of the arm segments. So we are using the original arm length for the solving of the IK in this setup, and we are using the current length of the arm that is a scaled version with the global scale, because we're using the world matrices of the upper arm FK world matrix, so that's the matrix that's sitting at the shoulder position, and the hand. And because we are scaling the rig as a whole, the distance gets shorter. So we can simply solve this by multiplying them with the inversion matrix of the main control, so setting them back to a unscaled version, and then calculating the current distance, and then all of the calculations in the IK solver are done as if the rig was not scaled. And because in the IK solver we in the end create a new matrix, the rotation plane matrix, where we multiply the upper arm local matrix width, and because we are basing this matrix off of the, let's see, upper control world matrix, this is already a matrix that has the scale of the global scale implemented inside of it. So if we look at this, the output of this matrix, in the second input, we can see that the scale is already set to the scale of the main control. So because we are first solving the IK and then multiplying it with this matrix, we are already scaling it down. So we have to solve the IK without the scaling of the main control. And we can simply do that by multiplying these matrices with the inversion world matrix of the main control, because the rest is already in unscaled versions of the arm length, because we are deriving these lengths from the guides, and the guides are still at the rest position. So for this we're going to have to add an extra connection to our module to the main control, the main module, and now we already have this connection because the parent and the input and the parent guide input of this module are connected to the output of the root module, but this is not where the arm normally should be connected. The arm should be connected to the shoulder. So we are going to leave the parent and the parent guide as they are, and we're going to add extra inputs to get the global scale of the root module. So we just create a new group, add it to the inputs, and we're going to call this the main input, and then duplicate it and call it the main guide input. And for now we're going to connect them to the same inputs as the parents, because they are now having the same parents, but later on we'll switch the parent for the arm to be the shoulder or the chest, for example. So if we look at where we are, these two nodes can have the same inputs as these two. So let's add them and graph the input connections to the inputs, like so. And then we can take the same outputs for now. So we are going to plug this one into the offset parent matrix of the main input, and we're going to take the main guide output, so it's the output nodes from the root module, and we're going to plug that in. So now these are the same and these are the same, but later on we're going to switch these connections to a different module. So this is correct now. We'll move this, and then in the IK panel we're going to multiply these matrices with the inverse world matrix, and thereby undoing the scale of the main control. So let's make a multi-matrix node, and then we multiply this matrix with the inverse of the current matrix of the main control, so the world inverse matrix, and then we plug this into there. So we're using the unscaled matrix to calculate the current length, and then we do the same thing for the hand IK control. So we take the world matrix, we plug it in, and then multiply it with the inverse world matrix, like so. And now you can see that the arm is solving the correct way. And let's check if it works in the smaller scale. It works in a larger scale as well. And if we switch to FK, and then the issues for the FK are gone as well. And that is because for the FK we used the same scaler to drive the individual segment lengths. So that's why the FK was going wrong, but now that is fixed as well. So let's reset that to 1 again. So basically what we're doing is we're saying, okay, no matter how the current scale of the rig is, we are going to use the unscaled version for solving the IK. The local matrices we have calculated are multiplied with the oriented rotation plane matrix, which already has the scale, and thereby correcting the scale for the IK solver. So let's rename these two. Okay, so I've renamed them to the same name as the input matrix, but then with no main scale attached to it. And we're only using this for the current length calculation. So a rotation doesn't matter either, because it's only using the relative positions to each other, so the distance between the two matrices. And if we see, we can graph the output of this node. So it's influencing two nodes. So it's the clamped length node and the length ratio node. And the length ratio node, I keep zooming out, it's quite annoying, is used for the scaler, the arm scaler. And this one feeds into the length scale enabler, and that is scaling the upper and lower arm segments. And if we now scale the arm or the whole rig to a larger scale, and if we were to reset the original connections, so bypassing the scaling, you will see that the arm length ratio is using the original length as it comes in from the guides and the current length as it is from the scaled matrices. So the new world position matrices, which are further apart, then the length ratio becomes a larger value. So we divide these and then in the length scalar we get the maximum value, and the maximum value of these two is 2.4 obviously. So then with the length scaling enabled, this feeds into the upper length and lower length scalars, and these are used for the FK. So that's why the FK gets blown out of proportion when we do not compensate for the scale. And for the IK, the issue was coming from the unscaled length in the IK solver. So let's set the connections to the scaled versions again, and then this problem is resolved because the scalar is back to 1. So let's reset the scale value to 1, and then we're back to our rig that is functioning correctly with rotation, translation, and scaling as well for both FK and IK. And with this we can move on to the next session.